Kia ora and welcome to this video on question 4 of the 2013 Scholl Calc exam. The question consists of two parts. First part is a complex numbers problem, which is kind of like a hard merit question, I guess. And part B involves this nasty proof and differential equation. And we're going to look at that in two different ways, one by integration and the other by differentiation. Okay, so first up, we're solving z to the n equals z, and we're told that n is a whole number between 2 and 9. So a case-by-case strategy is actually a good method to employ in this. What you do need to realise though is that z to the n equals z, irrespective of what n is, always has z equals 0 as a solution. So if n is between 2 and 9, which we're told it is, then z equals 0 is always a solution. I guess the only alternative to that would be if n was 0, then we'd have z to the 0, and 0 to the 0 is not equal to 0. So z equals 0 is a solution, and what that means is we can divide both sides of the equation by z. And that's key because the right hand side of this equation now becomes a constant, and we're solving a problem that's of this format: z to the z to the k equals r cis theta. And that's what makes this a merit question. So when we solve z to the k equals r cis theta, we use polar form because de Moivre's theorem allows us to use or to find roots of complex numbers. And n minus 1, the power, is just a whole number, because n is between 2 and 9. We're just considering different cases. So if n is equal to 2, then we're just solving z equals 1, z to the power of 1 equals 1. Okay, so that's clear that that's just z equals 1. If n is equal to 3, then we're solving z squared is equal to 1. That's equal to z is equal to 1, or z is equal to minus 1, but we've already seen the 1, so we don't want to double count that. N is equal to 4. Don't worry, we don't have to do this all the way up to 9. We're gonna spot some patterns in a sec. N equals 4 is going to be z cubed equals 1. There's 3 solutions to z cubed equals 1. A z is equal to 1, and then 2 other solutions that are equally spaced around the origin by 2 pi over 3. So z is equal to 1, well, we don't need to include that because we've already got it. And the others are going to be z is equal to cis 2 pi over 3, and z is equal to cis 4 pi over 3, or negative 2 pi over 3, depending on which way you go with your argument. N equals 5, that's going to be z to the 4 equals 1. Okay, that's going to have 4 solutions, starting at 1, all split 90 degrees apart. So that's going to be 1, which we've already got, negative 1, which we've already got, and then z is equal to I, and z is equal to minus I. N equals 6, z to the 5 equals 1. Okay, those solutions are all split by a fifth of 2 pi, so 360 divided by 5, 72 degrees. So those solutions, apart from the starting one of z equals 1, are all going to be different and ones that we haven't seen before. Z is equal to cis 2 pi over 5, cis 4 pi over 5, 6 pi over 5, and 8 pi over 5. Yeah, so they're new ones. N is equal to 7, z to the 6 equals 1. That's going to have, the starting point is starting point 1, of course, and then if we look at z cubed equals 1 to spot the pattern, Those three are all solutions of z to the 6 equals 1 as well. But then there will be another one there, -1, which we've already got, and another one in there. So rather than 2 pi over 3, we're splitting 2 pi by 6. So cis I'm going to just move these dudes up there. So we've got z is cis 2 pi over 6, or pi over 3. Z equals cis 4 pi over 6, or 2 pi over 3. We've already got that, like I was saying. So we've only got two new solutions, the one there and the one there. It's cis 2, 4, 6, 8, 10 pi over 6. Or cis 5 pi over 3. Okay, n equals 8. Z to the 7 equals 1. Apart from z equals 1, all of the other solutions are different because 7 is a prime number and we haven't seen any of the solutions again. So I'm not going to write them out this time. I'm just going to say 6 more. Okay, not 7 more because we've already got the 1. And n equals 9, well, that gives us z to the 8 equals 1. Those solutions are all solutions to z to the 4 equals 1. 1, 2, 3, 4. But there's 4 more in the gaps. And have we seen those before yet? No, because it's at 45 degrees, which is pi over 4. We have none of our solutions at pi over 4, so it's the 4 in the gaps there. So I'm just going to write 4 more. Okay, so how many solutions have we got in total? Because that was n equals 9 was the last relative we needed to consider. We've got z equals 0, 1, z is equal to 1, 2, -1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, oopsies, they're equivalent, 12, 13, plus another 10 makes 23. There's 23 solutions to the problem in total. Just being careful that we didn't double count any, and also using the patterns for 4 and 6 and how they related to 8. So 3 and 4 and how they related to 6 and 8. Okay, part B. Okay, we've got an expression, an equation. It's called the relativistic rocket equation. Show that this equation rearranges to delta V equals some stuff, where the stuff has got the hyperbolic tan function in it. So we've got this hyperbolic tan function, which is there, but essentially we just need to make delta V the subject of this equation, and at the moment it's trapped in there and it's trapped in there. So how are we going to get it out? We're going to have to log some stuff. Logging stuff will be able to bring the power down. It's going to be a linear equation for delta V, because delta V is just, it's just in there. It's not being squared, not being cubed, not being tanned or anything. It's inside. It's going to be a linear equation eventually. But the first step is actually to log both sides to get the power out of the problem. So m0 over m1, the ratio of two masses, 1 plus delta V over C, all divided by 1 minus delta V over C to the power of C over 2U. Okay, so log both sides using the natural log, because the problem we're trying to rearrange it involves E. So natural log power will come down the front of the natural log. And while I'm at this point, I'm also going to put the fractions together in this stuff. I've got c plus delta v all over c divided by c minus delta v all over c. Those c's cancel. So I've got ln m0 over m1, c over 2u, ln c plus delta v over c minus delta v. Now I need to isolate the delta v. I need to access this and get rid of the stuff all around it. So everything else goes to the other side of the equation. Timesing by 2u, dividing by c. 2u over c, ln m0 over m1 is ln c plus delta v over c minus delta v. Get rid of the ln, which is kind of weird because we put it there in the first place, but if I do that, I can take e to the function on both sides. Cancel. So we've got e to the 2u over c ln m0 over m1 equals c plus delta v c minus delta v. I'm just going to have a quick look at where I'm heading here. See how we've got this hyperbolic tan function, and the argument of it is this u over c ln m0 over m1, which I've actually just got here. U over c ln m0 over m1. I've just got an extra 2 in the front of it, which is cool because there is a 2 in the expression in front of the x there. Okay, so still trying to make delta v the subject of this equation. Move the c minus delta v up the top. Move the delta v stuff to the left-hand side and everything else to the right-hand side. No, I'm going to move delta v to the right-hand side just to avoid negatives. So I'm going to have c times this stuff again, minus a 1 on the left-hand side, and delta v on the right-hand side is a common factor, 1 plus, I'll put the plus 1 last, e to the 2e over c, ln m0 over m1 plus 1. Okay, and then lastly, to get the delta v on its own, divide both sides by that last bracket. Okay, so what have we got here? I'm going to highlight that thing in pink again, the u over c stuff. And I'm going to call that x. If x is equal to u over c ln m0 over m1, then what we have is delta v is c e to the 2x minus 1 over e to the 2x plus 1. Going back to the original proof of the right hand side, I've got that e to the 2x minus 1 over e to the 2x plus 1 quantity, and that's the hyperbolic tan of x. So delta v is equal to c times the hyperbolic tan of the pink expression, which I called x. So suffice to say that this is equal to c times the hyperbolic tan function of x, which c times the hyperbolic tan function u over c ln m0 over m1. And that's the proof done. Box, smiley face. Okay, pretty serious algebra there, but it all had a direction to it. The reason I use logs to bring the powers down, the reason I use natural log to bring the e into the expression, and then even to notice that the hyperbolic tan function was there, I just needed to replace that pink part with x to make it easier to notice. Okay, last part. The relativistic rocket equation is derived from the following differential equation, where u and c are constants. And so we've got this equation, and we're asked to show that log of m is equal to that stuff. Messy stuff is a solution to the equation. So I've mentioned this in earlier videos, but if you have a solution to a differential equation, you don't need to derive it yourself, because that would require integration. All you need to do is to differentiate that solution and show that it works in the differential equation. Okay, so we're going to do it that way because it generally is easier. We will look at integration as well because it's a good application of integration by parts. Integration by partial fractions, which is often comes up in scholarship as an extension. Okay, so second part BII, we have apparently the differential equation dmdv apparently the solution to this is ln m equals negative c over 2u times ln 1 plus v over c over 1 minus v over c. Okay, so that's an implicit solution because m is not the subject of it. We could take the e of both sides to turn it into m equals and then differentiate. But I think it's written in this form because implicit differentiation is a little bit tidier with it. So I need to differentiate, or I need to find dmdv. So if I differentiate this expression, I get 1 over m times dmdv. It's implicit differentiation. Log of stuff is 1 over stuff times the stuff differentiated. And on the right hand side, differing with respect to v, where c and u are constants. C is the speed of light. U in the question, you're told in the question that u is a constant. It will be related to speed as well, I imagine. Can't say I ever saw this equation in my degree. Let's just tidy this up a little bit. Doing exactly the same thing as I did in part 1. I'm going to write this as c plus v over c minus v by putting the fractions together and then cancelling the common denominators top and bottom. Okay, so to diff the right hand side, minus c over 2u stays there as a constant. Log differentiates to 1 over, so we get 1 over c plus v over c minus v. And then we need to times by the derivative of the inner function c plus v over c minus v, and that's quotient rule. Diff the top is 1 times the bottom c minus v, take away the derivative of the bottom, which is minus 1, it becomes a plus, times the top c plus v all over the bottom thing squared. Okay, and that's the whole thing differentiated. Now we can tidy up the stuff. Remember that we wanted to prove that dmdv was equal to the whole thing on the right hand side. So if we move the m up the top, what else have we got? Got minus c over 2u, so this is going to all tidy up really nicely. 1 over the fraction c plus v over c minus v, we just flip the fraction upside down. And then this last bracket, the numerator simplifies to 2c because the v's cancel. So we've got 2c over c minus v all squared. Okay, and then we play the cancellation game, good fun. C minus v there cancels one of the c minus v's bottom right. The 2's cancel. And okay, that's all so far. M times minus c squared over u times 1 over c plus v times c minus v. That's a difference of two squares. So actually I'm going to write that as c squared minus v squared. Okay, now it doesn't look like the form of our solution. The right hand side, we've got the minus and we've got the m. Okay, minus and we've got the m there. And we've got the u in the denominator, but then we've got c squared in the top, and we don't have that thing on the bottom. But if I minus m over u, if I write this in a slightly different way, times 1 over c squared minus v squared all over c squared, because I can put the fractions together in that bracket in the denominator, then it flips upside down as c squared over c squared minus v squared. So it looks like magic, but what I'm going to do here is go, just so the marker doesn't look at you and go, well, you've just fudged that. So I've got minus m over u. I'm going to divide the top by c squared, and I'm going to divide the bottom of the stuff by c squared. So I could put a note there and go dividing top and bottom by c squared. And that is, if I put some brackets around it, the answer to the question equals right hand side proven. So given the solution that we've got, if we differentiate the solution and tidy it up a bit, it turns out to be the right hand side of the differential equation. So therefore it is a solution to the differential equation. Okay, an alternative solution to solving this problem is to look at using partial fractions. If they expected you to do it this way, they would have given you a hint to solving it. But of course, this differential equation gave us the solution. So we didn't need to integrate, but it is possible to integrate. So if we start off with the dE again, and this time we separate the variables. So we can take the u up the top left, the minus m down bottom left, dm integral, and then the right hand side take the dv up the top. We've got 1 over 1 minus v squared over c squared dv. The denominator is a quadratic equation, and the numerator is constant, so it's not f dash over f. A substitution's not going to help us. The partial fractions will. The left-hand side anti-differentiates to minus u ln m. M is positive, so we don't need absolute value symbols there. And then u is a constant. The right-hand side, I'm just going to tidy it up a little bit by timesing top and bottom by c squared. And then I'm going to rewrite this using partial fractions. This is not the kind of video to help you with partial fractions. If you've never seen them before, I did explain it in an earlier video. You might be able to find it in the tags, or just search up on Google for some exercises. But what we're going to do is say, because the denominator of this expression factorizes c minus v, c plus v, difference of two squares, we can split this fraction into two parts where a and b are constants. And we can put this back together again and look at what we've got. We've got denominators that are the same, so therefore the numerator c squared must equal this numerator here. V is the variable in this expression because we're integrating with respect to v. C is a constant. So looking at that, we need c squared, a constant, to equal a plus b times c plus a plus b multiplied by a minus b multiplied by v, which is a linear function. Because the left-hand side doesn't have any v term in it, a minus b here must equal 0. So a has to equal b. And then the other term, the c squared is a constant, must equal the constant a plus b all times c. C is not 0. C is the speed of light, so we can rule that one out. Dividing both sides by c, we get c is equal to a plus b, but we know that's equal to 2a because a and b are the same. So that gives us a is equal to c over 2 and b is equal to c over 2. The constants a and b written in terms of c, and therefore this right-hand integral can turn into integrating c over 2 c minus v plus c over 2 c plus v dv. What's that achieved? Well, the integral now has linear functions in both fractions, denominator of both fractions, therefore we can anti-diff it using logs. Minus u ln m equals c over 2. Be careful this one, it's ln c minus v divided by -1, so we need a minus. And then this one's ln c plus v, and I'm not using absolute values again because c is the speed of light and c is bigger than v. However, at this point I do need an integration constant. I need a plus c. I've already used c. I need another letter of the alphabet, so let's go plus k. But that would just be one solution of many, and I don't have any information in this problem to find out, I don't believe I've got enough information to find out what that integration constant is. So I'm going to try my luck here and just go, let's assume it's 0. It's got to be something to do with how c and v relate and when v tends to c, but I'm not too sure. Didn't do it in my degree. So assuming that the integration constant 0, looking at the solution and where we're trying to head, the solution that they gave us a long time ago was ln m as the subject of it. Okay, it's there, ln m, and so we need to just make ln m the subject of our solution we've just arrived at, and that's ln m divided by minus u, so we've got minus c over 2u, and then we can put the logs together because we've got a log, we've actually got two logs subtracted there. We've got log of c plus v over c minus v. Two logs subtracted is the log of the division, and then we can divide top and bottom of that fraction by c. So that becomes 1 plus v over c, and that becomes 1 minus v over c. And that actually is the solution that we were looking for. Happy days. Just bear in mind that the hint for the partial fractions wasn't given to us, so we actually need to either memorize it or realize that the problem could be done by differentiation. If they wanted us to use integration, as I said, they would have given you the hint, but there's nothing stopping you using integration without the hint, except for the fact that you need to know it works. See you in the next one.